Let's solve another problem where we have to use our knowledge of entropy principles in order to find common properties of a process. Air within a piston cylinder assembly, initially at 30 psi and 510 degrees R, having a volume of 6 cubic feet, is compressed isentropically to a final volume of 1.2 cubic feet. Assuming the ideal gas model with K equals 1.4 for the air, determine A, the mass in pounds mass, B, the final pressure in PSI, C, the final temperature in degrees R, and D, the work in BTUs. So let's lay out our storyboard. We'll start with a schematic. We've got a piston cylinder assembly filled with air, and I'm drawing the boundary line around the air, so the air and only the air is our system. Here's the given data. At state 1, the air pressure is 30 psi, its temperature is 510 degrees R, and it has a volume of 6 cubic feet. Now it undergoes an isentropic compression, and we're going to decompose that here momentarily, to a final volume of 1.2 cubic feet. So let's model this. We know we're dealing with a closed system, and we'll ignore any changes in kinetic and potential energy as being insignificant. We'll treat the air as an ideal gas, and we're also going to assume that constant specific heats apply to this problem. We were given a value of K equals 1.4, and recall that K is just the ratio of specific heats. It's C sub P over C sub V. So if K is a constant, then the specific heats can be taken as constants. And we were told that this process is an isentropic process. And that's important for us to be able to calculate the answers that we're required to give. Isentropic, as you'll recall from a previous lesson, has 3 components. The change in entropy during the process is 0. The entropy production during the process is 0. And the heat transfer is 0. So it's a constant entropy problem. It's a reversible process because there's no entropy production. And it's an adiabatic process. And if we did not understand this concept of the isentropic process, we would not be able to solve this problem. We want to find the mass in pound mass, the final pressure in PSI, the final temperature in degrees R, and the work performed during the process. Let's draw this process on a TS diagram. State 1 has a temperature of 510 degrees R and a pressure of 30 psi. So I'm going to plot it where those 2 lines cross, and it has some specific entropy. Now, because the isentropic process tells us that delta S is 0, we know that state 2 on a TS diagram has to be directly above state 1, that S2 will equal S1. And it will exist at some pressure T2 and some pressure P2 that we are asked to find. So let's find the mass of the system using the ideal gas law. The ideal gas law states that PV is MRT. Let's rearrange this and we can solve for M, and we'll use state 1 conditions as our variables. So M is equal P1 V1 over R T1. Well, P1 is 30 pounds force per square inch. I'm going to convert that to square feet. And the initial volume is 6 cubic feet. The gas constant is the universal gas constant divided by the molecular weight, that quotient having units of foot-pounds force per pound mass R, times the temperature of 510 degrees R. Calculate that the mass is 0.953 pounds mass. Now, in thermodynamic textbooks, many relationships are given for different particular situations. And we have a very particular situation here. We have an ideal gas having constant specific heats for this process involved in an isentropic process. And in your thermodynamic textbook, you will find some relationships that apply to this exact condition. Again, the condition is an ideal gas with constant specific heats engaged in an isentropic process. And in that case, we have T2 over T1 is equal to V1 over V2 to the K minus 1 power. And P2 over P1 is equal to V1 over V2 to the K power. So we can use these equations to very easily solve for the final temperature and the final pressure. So the final temperature is just the initial temperature times the initial volume divided by the final volume to the K minus 1 power, where K is 1.4. And I get a final temperature of 970.9 degrees R. P2 is the initial pressure times the initial volume over final volume to the K power, where K is 1.4. And to get the final pressure is 285.6 psi. Now we can solve for the work by writing an energy balance. An energy balance, when we're ignoring changes in kinetic and potential energy, it's just that delta U is Q minus W. And of course, I can write delta U as U2 minus U1. Q is 0. Again, because it's an isentropic process, I know that it's an adiabatic process, and therefore Q is 0. So I can write the energy balance. It's just the work is equal to U1 minus U2. But U1 minus U2 can be written with constant specific heats for an ideal gas as C sub V times the mass times T1 minus T2. Therefore, the work is equal to CV times the mass times T1 minus T2. Well, I need to calculate C sub V. Well, C sub V for an ideal gas is just the gas constant divided by K minus 1. Again, the gas constant is the universal gas constant divided by the molecular weight for air, which is 28.97, and that quotient having units of foot-pounds force per pound mass R. I'm going to convert foot-pound force to BTU and divide by K minus 1, where K is 1.4. And I calculate that C sub V is 0.1714 BTUs per pound mass R. So continuing, I know that the work is C sub V times the mass times T1 minus T2. Well, we just calculated C sub V to be 0.1714 BTUs per pound mass R. We previously calculated that the mass was 0.953 pounds mass, and we have the original temperature of 510 degrees R, and we computed the final temperature as 970.9 degrees R. We calculate the work is minus 75.3 BTUs. We expected this negative because this is a compression process, and the negative indicates that work has to be added to the system in order for the process to take place. Now, there is an alternate solution for this work term. We know that this is an adiabatic process. It was described as isentropic, but that means that it's also adiabatic. And you may recall when we were studying polytropic processes, which have an equation PV to the n power is constant. When n is equal to k, the process, the polytropic process, will be an adiabatic one. So for an adiabatic process, we can say that PV to the k power is a constant. Now, the work is the integral of P dV, and again, previously, when n is not equal to 1, which it is not here, then we know that that integral can be solved as this algebraic expression that work is equal to P2V2 minus P1V1 all over 1 minus n, where n is equal to k. But for an ideal gas, PV is MRT. So we can replace this numerator with MR times T2 minus T1. And then work is that term over 1 minus n. So we can solve for the work this way. It's the mass, 0.953 pound mass, times the gas constant R, which is the universal gas constant divided by the molecular weight. And I'm going to convert that foot-pounds force to BTUs. And then times T2 minus T1, where T2 is 970.9 and T1 is 510 degrees R. All over 1 minus n, and since n equals k, it's 1 minus 1.4. And I calculate that the work required by this process is minus 75.3 BTUs, which is the exactly the same answer as we calculated using a different approach.